find the volume bounded by the paraboloid z equals 1 plus 2x squared plus 2y squared, and the plane z equals 7, only in the first octant. Well, let's draw a picture of what this is probably going to look like. Essentially, we have something like this. Here's the y-axis, x, and z. And we're going to limit ourselves to the first octant, which we know is going to be on the positive xy plane. Now, up here somewhere, let me erase that. Up here is going to be the plane z equals 7, so it's just basically a horizontal line, actually a plane, z equals 7. Oops, there's a 7. And then this paraboloid is going to be, well, a parabola. But obviously, when x and y are 0, this is going to be at 1. So my scaling is clearly all messed up. And this is going to be spinning about the z-axis here, but I'm only interested in this portion right here. So what's it going to look like? What's this region going to look like down here in the xy plane? Well, if I take a look at this and I simply solve it, I substitute 7 for z, I'll get 7 is equal to 1 plus 2x squared plus 2y squared, which obviously applies that 6 is equal to 2x squared plus 2y squared, which tells me that x squared plus y squared equals 3. Well, this is a circle with radius root 3. So it's going to be a quarter circle, or the radius here being square root of 3. That's what we're going to look like. Whoops, that's kind of a mess. Square root of 3. There we go. That's what's going to look like down here on the xy plane, projected up here. So what I want to do is set up my double integral. And really, I think this would be so much easier, once again, if I work with this in polar coordinates. To set it up without polar coordinates, I'm just going to say over the region. This is going to be 7 minus 1 plus 2x squared plus 2y squared dA, which is going to be this integral over this region of 7 minus 1, so I'm just going to write in 6. 6 minus 2x squared minus 2y squared dA. And I'm going to pull out a negative 2, and that's going to give me this double integral over my region of 6 minus 2 times x squared plus y squared dA, which, if I switch to polar coordinates now, that is r squared. So life just got really nice. So this double integral now that I know I'm going to polar coordinates, what's my angles here? I need to swing around through here. So my angle will be 0 to pi over 2. And my radius as such is going to range from 0 to root 3. And the function I'm going to be integrating is 6 minus 2r squared times r dr d theta, which obviously I would distribute that r to make the integral so much easier. Let's see, 6r minus 2r cubed dr d theta. So the first piece, I'm going to work with just this. This is going to be equal to 3r squared minus r to the 4th over 2, because the 4, the 2 cancels, r squared 2 cancels, gives me 3 up there. Evaluate from 0 to root 3, which is 3 times 3 is 9, minus 9 halves. So that's just going to give me 9 halves. So that's the first part. So then I need to integrate that from 0 to pi over 2 of 9/2 d theta, which is simply 9 theta over 2 from 0 to pi over 2, which is going to be 9 pi over 4. That's it.